Math here, bonding 3 Lewis structures and VSEPR shapes. VSEPR is a covalent bonding theory. It stands for valence shell electron pair repulsion. So what it basically says is when you have covalent molecules put together, that those electron pairs are going to repel each other to get as far away from each other as possible. And that's the natural shape of a covalent molecule. So let's look at a couple of examples I've got for you. These shapes are all based on the number of bonds and the number of lone pairs. That number combined, that's called the number of effective electron pairs. So if we look, 4 and 0 has 4 electron pairs. 3 and 1 has 4 electron pairs, 2 and 2. So all 3 of these have the same number of electron pairs, but because there are different numbers of bonds and lone pairs, they're all going to have different shapes. Now these words are kind of weird. Some of them are kind of strange. But let's work through as we just go across the periodic table. If I have a molecule of HI, or even better yet, if we just did this with one of our diatomics like H2 or I2, they would all kind of be the same shape. I would have one bond between 2 molecules. There's a nice looking little I2 molecule, and it's just an I and a bond in between. We're going to represent our bonds with either springs or sticks. And obviously the shape of this has to be linear. It's straight. You can't do anything with it. Well then how come when we move next to column 2, now I've got a magnesium in the center, and that's going to bond up with 2 bromines. So I put my magnesium in the middle, I draw my Lewis structure, put the bromines, get them as far away from each other as possible. That means they're going to be 180 degrees away, and you end up with a molecule that looks like that. A magnesium in the middle with a bromine and a bromine. Octets, 180 degree bond angles. So that's it when you have 2 bonds, no lone pairs, there's a linear structure for you. As we keep moving across the table to the group 13, we've skipped over the transition metals. I grabbed aluminum chloride as an example. So I put aluminum in the middle, I put 3 chlorines around it, and now I've got everybody as far away from each other as possible. This is called a trigonal because it does look like a triangle if you were to draw lines, but it's also planar. This is a flat molecule. There's no 3-dimensionality to this. It's linear, so we call this trigonal planar. That's 3 bonds, no lone pairs yet. Now we move next door from group 13 to group 14. Now this is 4 bonds, no lone pairs. This is going to make a tetrahedral shape, and methane's a great example of this, CH4. There's my carbons. Why don't I draw them as a cross? Why don't I try to make them 90 degrees? Well, because in reality, if I make it 3-dimensional, where I have an atom that's going back into the board and 2 that are coming out of the board, I can get this into a tetrahedral shape with a bond angle that's 109 degrees for a tetrahedral. That's going to be much further. See, if I try to make this into a 90 degree, I'm going to have to start twisting and bending. That's going to put a lot of energy into this. I don't want to do that. These are getting as far away from each other as they can. That's a tetrahedral shape. That's going to happen anytime you have a central atom from group 14 bonding up, 4 bonds, and no lone pairs. Now right next door to that is group 15, and now we start getting lone pairs. So this is going to make a shape called trigonal pyramidal. Very similar to our trigonal planar, but now we're going to add a lone pair on that. And so by adding that lone pair, this spring is going to be my lone pair. I have 2 electrons up here. These are really negative. They're going to repel and push this molecule down to form a triangular pyramid, a 3-dimensional shape. Nitrogen, phosphorus, anything in that group 15 is going to form that kind of shape. Moving next door now to group 16, now we're going to form 2 bonds and have 2 lone pairs, and that's going to be water. water forms it this way, and you're thinking, why don't you draw it like a cross? Draw it like a T so that it looks an addition sign. But it doesn't bond that way. My springs are my lone pairs, and my two bonded hydrogens are here. They're a little bit different geometry than our tetrahedral. Even though there are four, these electrons repel more, so that's going to make this angle even a little bit smaller. We're not going to get into bond angles right now, don't worry about that, but we do need to know that is a bent shape of water, and that's very important to the structure and the chemical behavior of water. So just remember, when you're looking, find out how many bonds, how many lone pairs, and then match up your shapes to go with it. I'm Smath. I hope this video helps you.